So at this point, we'll hand off to Maryam RAHNEMOONFAR. She's an associate professor of computer science engineering at Lehigh University, and she'll give us a talk on toward a foundation model for efficient damage assessment following natural disasters. Over to you, Maryam. Thank you.
Yeah, so hello everyone. My name is Maryam RAHNEMOONFAR. I'm associate professor at Lehigh University. So actually in this talk, I mainly want to discuss about one important application that foundation model, generative models, and tiny ML can be greatly useful and helpful. So we know that frequent and increasingly severe natural disasters are threatening human health, infrastructure, and natural systems. Only in 2023, our nation faced 28 weather and climate disaster events, which causes more than $1 billion losses. So the provision of accurate, timely, and understandable information has the potential to revolutionize disaster management. So for quick response and recovery in larger scale, actually access to aerial images are very important for the response team. And the emergence of small UAVs, along with some inexpensive sensors, present the opportunity to collect thousands of images after each natural disaster with high flexibility, easy maneuverability, which are very important for rapid response and recovery. But despite the huge amount of data that has been collected, there are not enough an efficient AI algorithm that can provide insight. So we need some multidisciplinary algorithm that actually advance real-time, generative, and interactive intelligence solutions. So in this talk, I'm going to discuss about the three parts that my lab has developed in last few years. The first part is when we can do real-time scene understanding, semantic segmentation on edge devices. Second, when we have interactable, interpretable, multimodal vision language model. So the the responder can be in contact with the UAVs or with any robot devices and can ask questions about the affected area. Is this area flooded, or can you show me the buildings that are flooded? Because actually this is important for the response team to allocate the resources efficiently and immediately after natural disasters. And also, although UAVs and optical imagery are helpful, but they may not be efficient because, for example, when you, in the case of fire, the whole area may be covered with the smoke. So aerial imagery and optical imagery cannot see. So we need additional sensors like synthetic aperture radar that can penetrate through the cloud, the smoke, and see underneath. Or for example, for the flood, we cannot, with optical imagery, we cannot see the flood under the vegetation, but radar can penetrate through the vegetation. We can see the flood underneath. So, but to actually develop this algorithm, the first thing that we noticed, there wasn't any AI-ready data set that we could use. So in my lab, we developed FloodNet and RescueNet to initiate this research. So the images were collected by my colleagues in the Center for Robot-Assisted Search and Rescue using small UAVs after several hurricanes, including Harvey and Michael. And in my lab, we developed this benchmark and data set. One of them was FloodNet, which it has classification label, semantic segmentation label, and VQAs. And for example, we can see where are the buildings, where are the flooded buildings, flooded road, and etc. Yeah, this is kind of more of higher resolution FloodNet. And also for the damage assessment, what kind of damage we have? Do we have no damage or medium damage or major damage, because as I said, again, for the response team, it is very important to allocate the buildings that have been totally destructed or have major damage. So maybe they can kind of run to that area, and maybe there are some people that are kind of need help, or so yeah, kind of detecting this in real time is very, very important. And yeah, this is for the VQA part, the type of questions that we develop. So for example, how many buildings are flooded, or is there any seriously damaged area, or etc. So for the real-time scene understanding and semantic segmentation, we kind of evaluate some of the encoder and decoder architecture and two-pathway architecture. So some of the segformers or hardener methods. And we kind of tested both on the floodnet and rescuenet. So here I'm showing the result for the floodnet, and as you can see, the transformers show high accuracy and also higher efficiency for semantic segmentation. But in addition to being real-time, we want our model to be interactive and not be task-specific, because existing models are task-specific. Either they can do classification or semantic segmentation or object detection, and there is also not any relationship between kind of different objects and neighborhoods, and they are not interactive. So the VQA parts in our research provide multimodal AI tasks. It provides diverse information from images depending on the question. It greatly helps with rapid response and recovery, and it can have a direct interaction with first responders and users. So for that, we develop supervised attention-based visual question answering for post-disaster, that you can see the detail in our paper. So here we have both CNN architecture and RNN, LSTM, and also we have some visual masks that actually help with the interpretability of our model. Because when you work with the actual community, not only your model should be accurate, but also it should be interpretable, and they need to have trust in your model. So for that, actually our model not only provides the answer that, for example, what is the level of building density in the image. So for example, our model provides that it's high, but also it shows the high interpretability. So it kind of highlights the buildings that are in the image, or for example, how many non-flooded buildings are there. So as you can see, for other models, it either highlights only some of the buildings, or it will highlight some other area. But for our model, it actually shows where it got the prediction. And etc. For example, is the road flooded? So for although all of the models provide answer no, so the road is not flooded, but our model actually highlights the road. So it's actually looking at the road and not, for example, on the grass or in other areas. So this was one component for interpretability, which is very important. And also in collaboration with Dr. Mohsen in lab, we actually make our VQA model very compact, that I think has to explain about this a little bit. And you can find more details in the paper that is coming up. So to expand that research, we also develop some diffusion models. So not only we want to be able to generate text for our image, and not only in the VQA format, but also in the kind of image captioning or image summarization. So we want our model to be able to kind of explain what is in the image, but also to kind of to address the issue of kind of unlabeled data set or kind of very few labeled data set. We want also to go back from text to image, and also sometimes for the awareness purposes. So we want to show that if Hurricane Harvey that happened in Texas will happen in Pennsylvania, how the roads look like or which area will be flooded. So it kind of show the awareness and prediction. So we kind of tested this diffusion models on only vegetation area or vegetation with some buildings and some in residential area with many buildings. So in kind of vegetation or vegetation with few buildings, it's kind of show higher accuracy comparing to a residential area, but the results are still very promising. All right, another area that actually my research lab has addressed is generative model, in the sense that when we have sensor that is actually collecting the data, but it has some limitation. So as I mentioned before, for example, if you have only optical imagery and looking at area after wildfire, the area may be completely covered with the smoke. So actually you cannot see the area. So you need to use some complementary sensor like SAR, synthetic aperture radar, that you can kind of onboard it on UAVs, but those data also are available through satellite with much lower price. So the idea is here that before fire and for some normal area, we have the correspondent synthetic aperture radar and optical data. What we can do when the fire happen actually, and we kind of have one type of imagery, but we are losing other type of imagery, or the other imagery like optical is not efficient, then you can kind of generate, using the generative model, you can generate what the kind of the post-fire data will look like. So based on the correspondence between the optical and synthetic aperture radar data before the fire or for other areas, you can kind of generate those for post-fire. So based on synthetic aperture radar, you can generate optical data, or based on optical data, you can generate the synthetic aperture radar. And you can, with that, actually, we created different indices. And for example, we could detect the burned area or generate burn severity mapping. But we kind of tested this for fire, but for flood, we have kind of the same scenario. This time, for example, under vegetation, you can see the flood with radar data, because it can again penetrate, because it has kind of lower bandwidth. It can penetrate through vegetation and see under vegetation or under kind of underneath the your surface, and but optical imagery have kind of this difficulty. So to kind of address all of this issue, actually, this is what we are currently working, and we are developing some foundation model that it can handle multiple disasters. So it's not limited only to flood or only to wildfire or only to hurricane. It can work on multiple scenarios and disaster. It can work on multimodal data, both the vision and language. It can work on heterogeneous sensors like optical, synthetic aperture radar, LiDAR. Another thing is that actually we have, although we kind of prepared some benchmark and data set, and we kind of create some label data, but for any new events, we have huge amount of unlabeled data. So we kind of want to use self-supervised algorithm and kind of based on transformers that we can kind of use a little bit of labeled data, but we can benefit from huge amount of unlabeled data. And we, at the same time, we want to make sure our model is efficient and real time, and hopefully it can also run on the edge. So if our radar image is kind of missing, or in some areas, or our optical imagery, or even our text is not complete, we can use a combination of this and foundation model, and using the encoder decoder structure to reconstruct the area and be able to generate the text for that. So I would like to acknowledge our sponsors and our colleagues in this regard. And if you have any question or comments, please let me know.
Fantastic. Well, thank you very much, Maryam. That was a really exciting talk. I think it shows the real-world value of tiny animal research and edge AI. One question, can you talk about, because it's so practical, can you talk about any organizations or ways that it's being used specifically? You gave a lot of examples, but any collaborations or deployments of what you've done that you can talk about?
Yeah, so actually we kind of had some collaboration with FEMA for kind of developing this model, but and actually we are working with the first responders, and that's kind of collect this data. But I mean, for the real deployment, it's still a way to go. So we haven't kind of.
Right, and because you're looking at UAVs, there's just another question. What kind of processing capability and power and payload can you really put on these types of devices? They're obviously meant for, flight and optimizing duration. What have you seen available to run these types of edge AI models on?
Yeah, so for this kind of UAVs, definitely if you don't have the battery life limits, they kind of can carry different types of sensors, and also we can do some real-time analysis. As I said, for the kind of practical and larger scale deployment model, this is still kind of ongoing, and so we have done the research part, and I would kind of welcome any collaboration from industry to kind of deploy this on larger scale.
Awesome. Well, it's a good thing you're here, and the audience can get in touch with you. With that, thank you very much, Maryam, for your talk and presentation and answer the questions. A big thank you again to all of our sponsors that make this possible. In particular, thank you to the executive strategic partners of TinyML, Qualcomm AI, advancing AI research to make efficient AI ubiquitous. Also, Sentient, making edge AI a reality. The platinum strategic partners, EmbedUR, Sony AI, deploy vision AI at the edge at scale. The gold strategic partners, ARM, Edge Impulse, Infineon, Renesas, ST Micro, and Synaptics. And the silver strategic partners, which we have here, AIZip, Arduino, BrainChip, Efficient, Greenwaves, Gravity, IMAX, Imagimob, Initera, Noda AI, NXP, Procter & Gamble, Schneider Electric, SensiML, Silicon Labs, and TDK. So that concludes our first day. Don't forget, we have a lot more action-packed agenda for tomorrow as well, starting at the same time. So that concludes our session for today. And thank you for joining, everyone. See you tomorrow.